So the Galton board is this device that has a container of metal beads at the bottom, an array of pegs in the middle, and then a bunch of bins at the bottom. So when you flip it, all those beads fall out. They hit that array of pegs and fall into these bins here. As you can see, this forms a normal distribution. As you can see, this clear curve here. The reason that is formed is because at each peg, a bead can either go left or right with a 50% probability each. There's approximately 50%. Probably not exactly the case for the real Galton board, but in my other video I simulated it, and in that case I assumed it was 50-50, which is what a lot of people do. So if you do that 50-50 trial at each layer, you form a binomial distribution. But if you have enough beads, the central limit theorem tells you that the distribution you form will be a normal distribution if you have enough trials, if you have enough beads in the case of the Galton board. And that is why we form a normal distribution or Gaussian instead of a binomial distribution. So in the sort of companion to this video, I showed and explained how to simulate the Galton board. What I did not show is a sort of proof to show that my simulation was correct. I made the point that I couldn't really check the simulation of the Galton board with the actual toy Galton board, because what I was actually simulating was an ideal Galton board. Since I assumed that the beads didn't bounce off pegs, miss any pegs, interact with each other, and other things that are probably not 100% accurate to the real Galton board. So I don't think in good conscience you could use this to check your simulation, even though you could probably get away with it, but I want it to be exact. So what I'm going to do in this video is I'm going to prove that my simulation is correct by deriving an equation for the probability of finding a bead along the bottom in any one bin. That's what I'm going to do in this video. Something very important to me is that if you make a simulation, you should check it somehow. Normally, I think you could check a simulation with data if you were to take data from this, but we're not exactly simulating this, so we can't really use this. So that's why I'm going into the exact probability territory, deriving an equation to check it. Because if you don't know that your simulation is accurate, then how can you use it? You want to be sure. So what we start out with is this equation for the binomial distribution. You can find this online. So P is the probability of going left, not right. I crossed that out. Forget about that. And Q is the probability of going right. Little n here is the number of Bernoulli 50-50 trials. So when a bead falls, it goes through some number of 50-50 probability trials as it goes down. Now capital X is defined as the number of quote-unquote successes, which I'll explain what that is. That's something I'm just going to define in the next couple steps. Everything else are technically our knowns. Like we know P, we know Q, we know N, technically. We just gotta specify them. For our second step, what we're gonna have to assume here is that P and Q both equal 0.5. Okay, so P equals Q, which equals 0.5. And that will simplify this greatly. I am only going to show it for PQ equal to 0.5. I'm not going to do it arbitrary for any probabilities, because the way I did my simulation is that I made it so you can input any P and any Q if you wanted to play around with it. But I'm just going to check it with 0.5. I think that's enough. So if we take this assumption and plug it in here, this equation is now simplified. So if we write out this with the 0.5s in there, what you'll notice if you know a little bit about math is that since these both have the same base, we can multiply them. So we can multiply this guy, including that, and this guy here. And if we multiply them, we can actually add their exponents. So we can add those. And so if you notice, the x's cancel out. You're just left with an n. So we can rewrite this. Now remember, 0.5 is just 1/2. So this turns out to be 1 over 2 to the n, where 1 to the n is 1. So this gets a lot more simplified. I didn't mention this is what's called a combination, which I will write out in just a minute. When I write out the combination, I get this with some factorials and 1 over 2 to the n. If you don't know what a factorial is, that's like 4 factorial, that's 4 times 3 times 2 times 1. It multiplies all the integers equal to and before it in a row. What about x? What is x here? What is x? X is technically the number of successes, which is really arbitrary. It's really whatever we want it to be. It can either be left or right. So for the sake of this, I'm going to assume, maybe because I'm right-handed, that the success will be right. So I'll rewrite this. So I rewrote this equation with an r. R is just the number of rights. So r is the number of times that a bead goes right. Okay, that's fine. It doesn't matter. You could choose left if you want, but it'll cancel out in the end. So now with this equation for our probability, we have r, which is an unknown. We don't know what r is. So how do we get r? R can be defined really simply. So r is the number of times you go right. L is the number of times a bead goes left. So if you assume when a bead moves left, it moves -1 to the left, and when a bead goes right, it moves +1 to the right. So we can write this as the final position, little x, can be defined as the number of rights times 1 plus the number of lefts times -1. So that's the final position. That's the final position of the bead. Pardon my writing if that's hard to see. So that's x equals that, which can be simplified to r minus L. Now there's also another very simple equation that we can write here. Now you can also say that little n, which is the number of layers and the number of trials that a bead goes through, little n is equal to r plus L, because there's no other choices. Number of rights plus number of lefts has to equal little n. Now this is wonderful information. What this is we have two equations and two unknowns, which is wonderful if you've done any math or physics in college or whatever. When you have two equations, two unknowns, that's wonderful because then you can solve for your unknowns. What we want to do is solve for r. We can do that. So if you do that, and I'm just going to fast forward through this a little bit, left, so the number of lefts is equal to little n minus little x over 2, and capital R is equal to x plus n over 2. Okay, so we have these two equations that define the number of rights and the number of lefts that a bead will take as it falls. So what I can do is plug that r straight into the equation for probability here, and I will do that. But I want to do something real quick. I want to just show you and explain to you something really interesting that this means here. So when beads fall down the Galton board, if they want to get to a certain bin, there are many, many different paths that you can take in order to get to that same bin. So if I wanted to get to this bin here, there's all sorts of different paths that I can take to get me there. But what these two equations are telling us is that for each bin along the bottom, so any one bin along the bottom, there's a unique combination of lefts and rights that it takes to get there. In other words, even if you take a different path to get to the same bin, you're always going to take the same number of lefts to get there, and you're always going to take the same number of rights to get there, no matter which path you take, which I find really interesting. Like, that's just something that's not really obvious, but it's true according to this. Anyways, that's a sort of tangent. So we can write the probability with our new definition of r here. See, now I'm putting in our definition for r, x plus n over 2, into our place for r. Now this looks a little complicated, and it sort of is, but it doesn't really matter because all we're going to do is plug in a value to it. But I can simplify this. If we find a common denominator here, then we could subtract these two. You notice that an n cancels. So here we have the equation for probability of finding a bead in any one of these bins here. If we want to find the probability, all we need to plug in is x, the position. So we could do this for all the positions of any one bin, and we could actually find all the probabilities that are required in order to get to any one of these bins. So we can make a plot of that, and I will. But so that's the general gist of how to get there. This is the equation. I did want to further note the difference between my simulation and the actual Galton board. I went over this in my main video, but I'll go over it again. We're basically simulating this triangular bit here. We're not simulating this extra stuff on the ends here. And these are a result. If a bead goes over here, that's because it misses a peg, or it bounces over it, or it hits other beads and it gets to over here. So I'm not simulating that part. I'm only simulating this triangular bit here. Because in the simulation, the furthest it could go out would be along this line. or along this line. So this is just another difference between our simulation and the actual Galton board, but then again, we're actually simulating an ideal Galton board, so it doesn't really matter in the long run. Now, if you watch the other video, or you kind of know what I did, where I just literally got a histogram that looks like this, you can actually get probabilities from this. All you need to do to get your simulated probabilities is to take the number of beads in a bin and divide by the total. You do that at each bin. So let's say you get the probability for this bin by taking the number of beads, divide by the total number of beads in the board. You just find the position of that bin and you plug it into this equation, and then you compare them. So what I'm going to do is I'm going to compare them in some code, which I'm not going to really go through the code since it actually gets a lot more complicated than the Galton board simulation in the other video where I did show the code. I'm going to show more or less how I got there, and I'm going to show my results of the comparison between the simulated probabilities and the exact probabilities. I did also want to explain something real quick that I explained in the other video, so if you already watched that video, you can skip ahead some amount of time. I just wanted to explain because when you make the Galton board simulation and you have x, what you define as x, it's going to make your histogram look a little funny, but it's fine. So if you have a simple Galton board here of n equals 3, if a bead falls and it can go right once, it can go right once again, it can go right once again, etc. You get these positions, x equals 0 right in the middle, then it moves right once, you get x equals 1, moves right once, moves x equals 2, x equals 3. So that's the position that the bead is at when it moves. After each time it moves, that's the position, and vice versa for the negatives. These are the bins here. What you notice is that you can only get into these bins. Well, these are the only bins there. You can only get into these positions, those being 1, 3, and -1 and -3 for n equals 3. What this means is that you can't get to every x. So in an equation, this tells you that x is equal to this. So minus n plus 2 up to n minus 2n. So these are all the possible x values that you can land. So those are these. These are the x values that you can actually land in. So with all that explained, I think I'm ready to show the results I got. I'm not going to show all my code because it just gets complicated and just messing around with arrays and lists and stuff. So it's kind of just annoying and boring. Go to my other video if you want to see the sort of base Galton board simulation code that I made, which I showed all of. Right now I have big N equals 12, 50,000 beads, stuff like that, 50-50 probability. You can see the other video. And then this is the function that I'm using to calculate the probabilities, the exact probabilities for the bins of the simulation. Using the math package, it's however you want to code it up, really. But you know, that's just kind of what it looks like if you want to steal it or whatever. But it's not too crazy. It's just literally what I wrote, the last thing I wrote, or one of the last things I wrote, that equation for probability just in code. So I was going to note on an effect where the higher big N you get, the lower and lower chance, less likely it is that you're going to see a bead go out that far. So what I mean is, like, if you have big N equals 100, the chances of a bead getting out to 100 is incredibly low. That's what I noticed. I was going to say, by looking at this equation here, you could see that, but it's not crazy obvious. For example, I'm not sure if, I think factorial of n grows faster than 2 to the n, but then there's also these other factors. So I do think that the probability does decrease as you go out for bigger big N, but I can't really demonstrate that. So I do think that the bigger the big N, the less likely it is that you're going to be able to get out that far, and so the probability is going to be very low from what I saw, but I can't really justify that. Other than that's just kind of what I saw. In this code and my other code for my other video, I used big N equals 12, which is the big N for my Galton board. So you can probably use a bit bigger, smaller as well, but don't get too big, otherwise you're going to run into errors. So I ran my other code, which is just the Galton board simulation. You could see, note how, like I said, you have these empty bins, and that's just because of the way we define X, and you're only going to find beads in these specific bins. So what I did is I took each bin and took the bin contents divided by the total. So the total bin contents, and that's the probability, the simulated probability. Then I took that position and I plugged it into the equation, that probs function that I made. I plugged it in to get an exact probability. I plotted both of those and then took the difference and plotted that as well. So this is what I have. On the left, you see the same thing. And on the right, you have the probabilities. And so the red, sort of orange, what is that? Red, sort of orange is the simulated probabilities. Blue is the exact. And then that's the difference. You can see the difference is right along with 0, which is great. And they're all very, very close to each other. I bet if I increase the number of beads and stuff, it would be even closer. But yeah, so this proves that my simulation is doing what it's supposed to be doing, that it's right, and it's working, which is great. Just remember that we're not simulating the Galton board, really we're simulating an ideal case, and so this is just showing that our ideal case is right. And so we can play around with that and know that we're doing it right. I ran it for 100,000 now, and it seems that they're even closer to, in some of the cases, yeah, in really all the cases they are closer. So hey. So again, the point of the video was to show the importance of, if you're making a simulation, to check it, and also, of course, specifically checking the Galton board simulation, which involves some probabilities and statistics, which is cool. All right, so that's all I have for this. I hope you enjoyed. If you did, leave a like if you want, or subscribe. I should hopefully be making more stuff similar to this, or just whatever I come up with at this point. Also check out the other video to this, the main video to this if you want, which just goes into the Galton board simulation specifically and more in depth. And I think you could find something interesting there. Anyways, I think that's all I have. So, bye.